Let's continue now and actually do an example. And this time I think for the example we'll take the most challenging one. If you can understand this one, you can understand everything about the F. And so let's just suppose that we've got a null hypothesis, H naught, that the systolic blood pressure for women and the systolic blood pressure for men are the same. That's my null hypothesis of no difference. Now if these two are the same, then they'd be equal to 1. Alternate hypothesis, there's somebody out there that's making the claim that the sigma square for women and the sigma square for men are in fact not the same. Now just a note right this minute, and we'll come back to it later. If what we're testing is equals versus not equals, I think it wouldn't matter which way we had these. I could put the m on the top, sigma square m, sigma square w on the bottom, or I could do it the way I've done it. Here's how I'm going to decide which way to do that. I'm going to peek at my data that I've collected, and I'm going to arrange these two so that my test statistic will be in the upper tail. I want my test statistic to be greater than 1. And as an example, just suppose here that I had in my sample, I had men 16 and women. They're independent samples, and so they actually don't have to be the same, and in fact they're not. So suppose I had 13 women in my sample, and then suppose that I had a variance in my blood pressure for men of, now what I obtained was a standard deviation 8.864, so I'll indicate that as squared to make a variance out of it, and an S squared women, and that was a 9.9176, 9.9176 squared. I want to test and see if these are equal, but notice that if I put the women's variance on top and the men's on the bottom, then their ratio is going to be greater than 1, and that's going to force my test statistic to be in the upper tail. And I want to force my test statistic to be in the upper tail because those tables in the back of our book are only upper tail tables. So we're going to come back to this in just a second, but there's our initial setup. Now I've got an equal versus not equal, and so it's no surprise to us, because we've been doing this for some time now, that this is a two-tail test. A two-tail test, and we need an alpha value. Well, again, a common alpha value would be alpha equal to 0.05. So I may have an alpha value equal to 0.05. And I'm going to find the critical region. Now it's a two-tail test, so really it's plural, it's critical regions. So here's my horizontal axis. I know that the F distribution starts at 0. It's always non-negative. It's always skewed right. It's always non-symmetrical. So it might look something like that. Now what about critical values? Well, it's a two-tail test, and so I'm going to split the critical value between the upper tail and the lower tail. And I'm going to have an alpha by 2 in the lower tail. Now if alpha is 0.5, this would be an 0.25, half of the alpha. And I'm going to have an alpha of 0.25 in the upper tail. Need to find the critical values actually. So here's a critical value down here, and here's a critical value up here. Now the critical value here, which F would this be? This would be F, degrees of freedom numerator. Well, I've got the women on top. I have 13 women in the sample, so my degrees of freedom numerator would be 12. Denominator is men. I have 16 men in the sample. My degrees of freedom would be the sample size less 1, so that would be a 12, 15. So this is the particular F distribution. If I would go to the second table of F, and that would be a table for an alpha equal to 0.25, and then find degrees of freedom numerator, and degrees of freedom numerator would be across the top. That would be a 12, and then down the side I'll find degrees of freedom denominator 15. At the intersection I'll find my critical value, the guy that goes right here, and it is a 2.96. So this critical value is 2.96, and everything above that is going to be in the critical region. So there's a critical region, and anything down here is in a critical region. I haven't found this guy yet. And anything that is in here, this is the region of acceptance, where we have to accept the null hypothesis. And so this is a classical test where we're going to be using critical regions and critical values. This guy I haven't found yet. I know it's down here, but I don't really need to find it. This is it's the correct alpha for a two-tail test at 0.5. It's the correct critical value for the upper tail. And see, by choosing to put women on top and men on the bottom, I've looked at my data. If there's a significant difference, since the women on the top, women over the men, is going to be greater than 1, if there's a critical difference, it's going to be felt in the upper tail. So while I know this is down here, I don't really need to solve for it. And that just simplifies this computation a lot. So I'll leave it down here indicated, and we're going to find now the value of our test statistic. So let's pick a new color and calculate the value of our test statistic. And so the F observed is going to be 9.9176 squared over 7.8864 squared is equal to, and that's a calculator problem if I ever saw one, and it's 1.581. 1.581, and that's what my calculator gave me. Well, here's the critical value, 2.96. A 1.581 would be right in here somewhere, certainly to the left of that critical value, not as far down as this critical value, but this is my critical value, 2.96, and this is my observed value of F. So that's the observed value of F. This is not in critical region, and so we have to fail to reject. Now, the lesson here is that I can always force this test into the upper tail, and so the tables that I have in the back of the book, which give me only upper tail critical values, are perfectly adequate. That's all that we really need. We've done our first F test. We could use our calculator and come up with a prob value. So if we were to do that, my prob value would be equal to 2 times the probability that F is greater than the observed value of F, 1.581. Now remember, it's a 2 times because it's a two-tail test. And this value I'm going to get from my graphing calculator or from Minitab, and that's going to be 2 times 0.1991. I just asked my calculator to calculate this probability for me. I had to tell it the F I wanted was the F with degrees of freedom 12 and 15. It gave me the 0.1991 multiplied by 2, and that's a 0.398. The p-value to complete the test is compared to alpha, that is 0.398, is compared to my alpha, and the 398 is, my alpha is 0.5. 398 is greater than alpha, and so I fail to reject H naught. And of course, I fail to reject up here, fail to reject down here. They always go the same way. All right, I think that's enough to get you started. I'm going to assign you a few problems, and I'll have a merry time at the dentist tomorrow, and I will see you on Monday. Email me if you have any questions. Enjoy the weekend. Thank you.